Hello, my name's Kaylee and I am here to show you Rush's AI Drughunter. Now, I'm going to put a link down here where you can actually go and access this and talk to it so that you don't have to take this stuff from me, you can go try it out yourself. But we released this bad boy about 2 weeks ago, so he's very much still learning and growing. We are adding new features every single week based on what scientists tell us they need. And this AI is designed to augment and accelerate scientists. It's not here to replace anyone. I personally don't think that anything will be replacing scientists for a very long time, but I do think that it's incredibly important to use all the technology we can to make scientists as productive and powerful as possible. And that's what we're doing here. That's what Rush is about. So I'm going to take you through a process that we might go through with Walter. We named the AI Drughunter Walter. I'll let you guess why. I'll take you through a process with Walter that we might go through to find some potential small molecule drugs for NPC disease, which is a neurodegenerative rare disease. So I actually know from some previous conversations with Walter that there is a link between transmembrane 97 and NPC disease. So I'm going to ask him to go and find me the info on that. Awesome. So Walter has gone into the literature. He's found this paper that I was thinking about, and we can click to see the references, which found that if you can inhibit transmembrane 97, it can increase NPC1 protein, and that can help to address NPC disease. So that's very good. So now my goal is, okay, let's see if we can find something that would inhibit transmembrane 97. So let's ask, are there any known small molecule inhibitors of transmembrane 97? That's a good place to start. And while Walter is thinking about that, I'm going to make a new chat and we're going to say, are there any structures, oh, bit of a typo, that's fine, Walter can figure it out, of human transmembrane 97 in the PDB. And we'll let him search. We'll go back to our other channel. Sometimes Walter takes a while to think because he's doing, as you can see, quite extensive gathering of data from a variety of different sources and then verifying stuff. So we'll give him a moment. Okay, cool. He's given us a list of known small molecule inhibitors. One of them is already a drug, haloperidol, so that's interesting, and then a bunch of DOIs we can check out. So let's say, can you find some structurally, again, typo, he'll figure it out, small molecules to how do I spell it, haloperidol. Awesome. So Walter has said, yes, you can do this similarity search run, and that is going to find structurally similar small molecules in the enamine compound library based on the Tanimoto similarity. So I just press go, and as you can see, this is already running. This is going to be running on supercomputers in the background, but the runs can take a few minutes to finish, depending on what you're doing. If you're screening a huge library, it can take a couple days, a few hours, depends what you're doing. Oh, but this has already come through. Cool. So I'm going to press pin results, and they're going to come up here. And I'm going to zoom in a little bit, and so we can see all of our results of the structurally similar molecules. So now I'm hoping that Walter will have found me a good structure. Okay, so there are no structures of human transmembrane 97. So what I will do is I'll say, can you predict the structure of transmembrane 97? So Walter has gone and found the sequence of transmembrane 97 for us and drafted a structure prediction run, so I'm going to press go. So Walter will be using Boltz 2 for structure prediction at this point. We are very thoughtful about what software and what tools we give to Walter to run. We always have our computational chemists do a really careful evaluation before we add any new capabilities to Walter to make sure that the computational strategies he's using to get his results are carefully benchmarked and are considered to be reliable. And if you ask Walter about what he is using to get his results. He should be able to tell you exactly what computational tool he's using, and for anything that's open source, he should be able to give you a URL so you can go check out the paper or go check out the GitHub and look at the benchmarking that's been done. We also use some proprietary software, particularly our quantum chemistry software, because we have a lot of expertise in that area, and that has been proven and benchmarked. So Walter is still going on structure prediction, but I actually did do a structure prediction run on this earlier, so here's something I prepared earlier. I'm going to press pin results on this, and we can see he's given us a predicted structure. And so now what I can do is I can select all of my similar molecules to haloperidol, and I can say I want to dock all of these to this structure, and I want to get a predicted binding energy for all of these. If we press new run, docking, oh, it's gone over here, and I'm going to say this TMM97, this one, and we'll just say predict the most likely binding site for me, and I'm just going to press go. I'm not actually going to run this one right now though, because this docking will take a while. There's a lot of molecules here. So again, in the interests of the demo, I'm going to get something I prepared earlier. So here are my results from docking these haloperidol analogs to the predicted structure of transmembrane 97 a bit earlier. And I'm going to press full results, and I can see all of the different small molecules. I can see their predicted binding pose, I can see their predicted binding energy, and I can see the CNN score. Now this CNN score gives us a confidence level for how confident we are in this predicted binding energy. So when we're using the platform, we generally filter for confidence scores above 0.7. We don't take into account the things below, and ideally we want a confidence score above 0.8. So a lot of these have quite a good confidence score. For the binding energy, this is a relative measure, so the more negative the better. And we can use this to relatively prioritize which of these molecules are going to be more strongly binding, or which are predicted to bind more strongly than the others. And that gives us a way of prioritizing which compounds are we actually going to take into a lab so that we can use our resources really, really efficiently and really targeted in the lab. You can also download the data into an Excel file if you want to do some more data analysis. And yeah, I'm going to leave it there because I want to keep this short, but that's just an example of the kind of conversation that you can have with Walter, where he can bring in the right computational tools to get you from very little information to a ranked list of potentially interesting small molecules to take for further research. Again, I'm going to put a link down here somewhere that you can use to go and check it out yourself. You don't have to take any of this from me. Go and try it, see how Walter does. Any information that you give to Walter is completely confidential. All of the IP belongs to you. We're not going to take that information and do anything with it. That's all embedded in our terms and conditions. And again, we are building features into this really quickly based on what scientists tell us they need. So have a look at how it goes. Tell us what doesn't work. Tell us what you need from Walter that he can't do already, and we can make that happen. And that's it from me. Thank you guys so much for hanging out.